Ever wonder how a platform like Twitter can handle, I don't know, 500 million tweets a day without the whole thing just falling apart? Well, you're in the right place. A huge piece of that magic comes down to solving one surprisingly tricky problem: how to create unique IDs. So let's set the scene. Imagine your application is a massive success. You've got servers all over the globe, all trying to write data at the exact same time. How in the world do you give every single tweet, every user action, every log entry an ID that is totally unique and ideally sortable by time without creating some central coordinator that grinds the whole system to a halt? That's the big question we're going to tackle today. Before we start looking at solutions, we've got to define the finish line, right? What does a perfect ID generation system actually need to do? Let's lay out the rules of the game. Okay, so our perfect ID has 5 key traits. First, and this is non-negotiable, it has to be absolutely unique. No duplicates, ever. Second, it needs to be sortable by time. This is a huge deal for databases because it makes looking up data by when it was created incredibly fast. Third, the system has to be highly available and scalable. It can't have a single point of failure. Fourth, generating an ID has to be lightning fast, super low latency. And finally, we want to pack all of this goodness into a simple 64-bit number. Why? Because databases are just way more efficient working with standard integer sizes. It makes everything faster. All right, now that we know what we're aiming for, let's look at the usual suspects, the common ways people try to solve this, and see why they just don't cut it in a big distributed world. This is where it gets really interesting. So the first thing many of us reach for is the good old database auto-incrementing primary key. And look, in a simple single database setup, it works just fine. But the moment you have multiple database servers, it completely falls apart. You're either stuck with one server handing out all the IDs, which creates a massive bottleneck, or you have to do weird tricks like offsets. One server only makes even numbers, another only makes odd numbers, but then your IDs are no longer sorted chronologically. Okay, fine. What about UUIDs? They are, by definition, universally unique. Problem solved, right? Well, not so fast. They've got 2 major flaws for what we need. First, they're not time sortable at all. They're basically random. And second, that randomness is actually terrible for your database. Think of it like an encyclopedia. Auto-increment is like adding new entries neatly at the end. A UUID is like trying to insert a new page randomly in the middle every single time. The database has to constantly reshuffle its index. We call that index fragmentation, and it will absolutely kill your write performance. Well, hey, if sorting by time is so important, why not just use a timestamp? Simple, right? The problem is, in any high-traffic system, it's not just possible, it's pretty much guaranteed that 2 different servers will try to create an ID in the exact same millisecond. That means you get duplicate IDs, which breaks our #1 rule. It's just not unique enough. So, after seeing all the ways things can go wrong, it is time for the elegant solution. This is the approach that the engineers at Twitter developed to solve this exact problem for their tweet IDs, and they called it Snowflake. The absolute genius of Snowflake is how it combines everything we need into one compact 64-bit number. It's all done with some really clever bit manipulation. You're basically treating that 64-bit number not as a single value, but as a collection of smaller numbers all packed together right there on the server that's generating the ID. Let's pop the hood and see how this thing is actually built. This is where the magic happens. That 64-bit number is really made of 5 different pieces. The very first bit is just a sign bit, kept at 0 to make sure the number is always positive. Simple enough? The next 41 bits, that's the most important part. It's a timestamp, measured in milliseconds. Then we have 5 bits for a data center ID, and another 5 for a machine ID. This is how we know where an ID came from. And finally, those last 12 bits are a sequence number, which is our tiebreaker for any IDs created on the exact same machine in the exact same millisecond. And the process to generate one? It's beautifully simple. A server just takes the current time, subtracts a starting point we call an epoch, and then uses a super fast operation called bit shifting to slide those numbers into their designated slots. If you're a Go developer, you're familiar with this. It's that left shift operator. It's an incredibly efficient, low-level thing to do. And if another ID is requested in the same millisecond, it just ticks that sequence number up by 1. It's all done in memory, crazy fast. And just like that, Snowflake checks every single one of our boxes. It's unique because that combination of timestamp, machine ID, and sequence can't ever be duplicated. It's sortable because the timestamp is the biggest part of the number. It's scalable because each server generates its own IDs independently, no talking to each other. It's super performant because it's just a bit of bit shifting, and it's a perfect 64-bit integer. It's just elegant. And the capacity this design gives you is incredible. Those 41 bits for the timestamp, that gives the entire system a lifespan of about 69 years before you'd ever have to reset your starting point, your epoch. Not bad. Then you've got the data center and machine ID bits. You combine those, and you can have over 1,000 unique servers all generating IDs at the same time without ever stepping on each other's toes. And here's the really mind-blowing part. That final 12-bit sequence number means that each one of those servers can produce over 4,000 unique IDs per millisecond. The scale is just staggering. So the system seems pretty much perfect, right? But there is one subtle little gotcha that every senior engineer needs to worry about. The whole beautiful design rests on one critical assumption. The time is always moving forward consistently across all your servers. This potential issue is called clock skew. It's what happens when the clocks on your servers just drift apart. You know, if one server's clock runs a little fast, it might generate IDs that look like they're from the future. But even worse, if a clock ever jumps backward, you could start generating duplicate IDs, which, as we know, violates our #1 rule. Thankfully, the solution is a well-established industry standard. You just use Network Time Protocol, or NTP, to constantly synchronize the clocks on all your machines. In fact, a robust implementation, like you'll find in some popular Go libraries for Snowflake, will have a safeguard. It will flat out refuse to generate an ID if it detects its own system clock has moved backward. So, we've seen how Snowflake was this brilliant, elegant solution for the web of a decade ago, but its design kind of assumes you have these long-running servers with stable machine IDs. This leaves us with a final thought to chew on. In today's world of serverless functions and containers that can appear and disappear in seconds, how would you adapt this design? What would you change to make it work for the cloud of today?